and welcome to another episode of Double Award Physics. In this one we're going to look at section 2.1.1, which is the start of the waves section. Okay, so in 2.1.1 basically we have to describe the different types of waves. Now there are two different types of waves. There's the uppy downy type and the side to sidey kind of forward backwards type. Okay, now the uppy downy type, you can't call uppy downy because that's non-scientific. We call them transverse waves. Okay, and this would be an example of a transverse wave here. Okay, the wave goes downwards and then upwards and then downwards and then upwards and then downwards and then upwards. Okay, but that's not what makes it transverse. What makes it transverse is the direction of flow of energy compared to the direction of the disturbance that made it. Okay, so in this one, imagine you're making this wave. How you make this wave is you grab one end of it and you make your hand go up, and then you make your hand go back down again. Okay, and that creates a little pulse that sends the wave this way. Okay, but the wave energy is going this way. Okay, because if I send this down somebody at the end of this gets hit by this wave. Okay, so the energy goes this way. My hand or my disturbance or whatever it is, if I'm jumping up and down, this makes this wave. I could be moving my hand up and down. I could be having some form of electrical oscillator. I could have anything, but it goes up and down. Wave goes that way. Okay, so in this respect, this is energy going this way, and this is my disturbance. Okay, now if you are a transverse wave, then the disturbance is always at right angles to the direction of energy flow. Okay, so that's the definition of a transverse wave. That transverse, the energy travels at right angles to the direction of the disturbance. Okay, that's your transverse wave. Happy with that? Good. Okay, now examples of transverse waves. Things like normal water waves. This is like the surface wave on a water. Okay, you got a big crest, you got a surfer in here, you got a trough in there, you've got a dead surfer later on. Okay, that's a transverse wave. More importantly, all of the waves in the electromagnetic spectrum are also transverse. So if you asked an exam to give two examples of transverse waves, just pick two of these. Ultraviolet, visible light, done. X-rays, microwaves, move on to the next one. Okay, so every single one of these is a transverse wave. Right, I need to be able to get these in the correct order, but that's for later on. Okay, good. Now the next type of wave that we're looking at is longitudinal waves. Longitudinal waves are slightly different. They're created by kind of pushing backwards and forwards against something. Okay, so to create this wave, what I have to do is I have to kind of push that way and then pull my hand back that way. Okay, so that's like a slinky spring. If you had a slinky spring laid out all across the ground, so this was, you were looking at it from above here, and then if you push the slinky, you'll get a little area where it's compressed, a little area where it's spread out. Okay, we call this area a compression area. Grab the note tool here. So this is a compression. These spread out areas we call rarefactions. Okay, so compression, rarefaction. And this is a longitudinal wave. And the primary reason that this is a longitudinal wave is if you think about the energy direction of this, again, if I have something traveling this way, then something on the end of here gets hit by this wave. So the energy travels this way. Okay, now if I take those arrows and compare them to each other, then this arrow, and this arrow, because they are longitudinal waves, longitudinal, then the direction of energy flow is parallel to the direction of the disturbance. Okay, because this line, and this line are parallel. Compare that to our previous situation where the transverse wave it was perpendicular to, or at right angles for the non-mathematicians amongst you. This time it is parallel. This line and this line, if we were to continue them forever, would never ever meet. So they're parallel. Okay, best example of longitudinal wave that we see in nature is a sound wave. Okay, so a speaker creates a compression in the air, That compression hits other particles, spreads them out, pushes them back together, sends a little pressure wave towards your ear where you can hear it. The specification says that the two types of wave that you need to know for longitudinal are sound waves and, imaginatively enough, ultrasound waves. Okay. Now, if you get stuck in an exam and you can't remember sound and ultrasound, for a start, you probably shouldn't be in that exam. But the third one you can go for is a push-pull on a slinky spring. Okay. Alright, and that's all there is to it, really. What we've got to talk about now is the various particles in the medium. Okay, so if now we look at the whole wave. We say the wave goes up and down, the energy travels this way. Imagine we were like a single particle in a transverse wave. So let's get ourselves a little single particle. Okay, let's get a few of his friends. Okay, now we're close enough together that we're kind of we're not necessarily molecularly bonded, but we definitely affect each other. Okay, so we're going to look at this guy. Call him Roy. I'm going to call him Roy. You can call him whatever you like, because he's an imaginary particle, and you can call him whatever you want, because he's not going to get upset. So here comes Roy. Now I create a disturbance at this end. Okay, so I push this guy up beside him. Okay, he gets pulled up. Okay, as a result, the kind of attraction between this guy and Roy pulls Roy upwards. Okay, not quite to the same height, conservation of energy and all that, but you know, upwards. That drags this guy up, drags this guy up, drags this guy up. Okay, so you get the start of your wave. This guy can't stay upwards forever, so he falls back downwards. Roy comes with him. He comes with him. He comes with him, and so forth. Okay, as a result, you get this up-down pattern. And now specifically, that makes us our wave. Okay, so we end up, if we do this over and over again, then we get the whole thing goes up and down and up and down, and you get kind of a Tourette's looking transverse wave. But here, what we have, if we just consider Roy, he moves upwards and then downwards and then upwards and then downwards. So for a single transverse wave, then what happens is that for the particle moves either upwards or left or right, or depending on how you've made the wave. We've made it upwards, so the particle moves upwards from its rest position, then returns through its rest position and repeats as long as the disturbance continues. It will eventually return to the rest position. Okay, now that last bit is important, okay, because that's what makes it a wave. Okay, rather than it being a bullet or something like that, the fact that it will eventually return to its rest position, and all of these particles will return to their rest position, is what waves are all about. Okay, a wave will transfer energy from one point to the other with no overall movement of stuff. Okay, when this wave has gone past, all these particles are back where they started, just energy has travelled from one place to another. Okay, which is different to throwing a tennis ball at someone. Okay, you hit them with a tennis ball, they say, ow, energy is transferred, but so is a tennis ball. If you fire energy down a wave, you're still holding the bit of the wave that you started with. Alright? Good. Okay, same deal is for longitudinal waves. If we delete this out, okay, return ourselves to our original position and change the direction of our oscillation to that, and then of course it could be backwards as well. Then let's do it backwards. Well, backwards. Okay, this guy gets pulled this way. Okay, which pulls Roy with them, which pulls this one, which pulls this one. Okay, and then that one gets released, so pushes that, pushes that, pushes that, pushes that, pushes that. Okay, and again the particle moves this way. We started with to the left from its rest position, then returns through its rest position to the right, I suppose, and repeats as long as the disturbance continues. And eventually it will return to its rest position as well. Okay, making that a wave. Are we happy? I hope so, and I'll see you next time.